Evaluate exponential functions with bases of e or 10 at numerical values. There are two special bases we're going to address. The first is base 10. And if your function is an exponential function of base 10, they're very quick to evaluate, especially when you evaluate at integers. For example, if I go ahead and just begin smack in the middle of this, I would evaluate by putting each of these inputs in for x. So I'll start by putting a 0 in for x. And anything to the 0 is?
1.
1. Now you're saying, man, there's a lot of problems to evaluate, but it's going to be very fast. A, I have a calculator, and B, I don't need a calculator most of the time. If I go ahead and substitute in a 1 for x, I would have 10 to the first, and 10 to the first is?
10.
10. If I substitute in a 2 for x, well, I guess 10 squared is?
100.
10 times 10. And very quickly I notice something, which is this number here, which is the exponent. If it's a positive integer, like 1, 2, 3, 4, 5, that's the number of zeros that follow the 1. So I don't mean to do this out of order, but I will. 10 cubed, I can go ahead and find very quickly. 10 cubed is what? It's going to be?
1,000.
1,000. And if I wrote up 10 to the 15th, you'd write a 1 down and about 15 zeros, wouldn't you?
Yes, you would.
Yes, you would. Now 10 to the 2.5, that's a little harder. I got to turn to my calculator. You have to go ahead and tell me what 10 to the 2.5 is.
That is 316.23, roughly.
Okay, so if you rounded to 2 decimal places, 0.23. So I use these approximation symbols. But this should feel correct because 10 squared is what? 10 squared is?
100.
10 squared is 100. 10 cubed is?
1,000.
So 10 to the 2.5 should be somewhere between them.
Should be, yeah.
And 316.23-ish is somewhere between them. Now with the negative exponents, that just flips the base. So if I go ahead and substitute in a negative 2 for x, I have 10 to the negative 2, but I'm seeing 1 over 10 squared. I flip the base and I remove the negative sign. And I know what 10 squared is. 10 squared is?
100.
So the output here would be 1 over 100. And similarly, you can kind of read where I'm going here. 10 to the negative 1 is 1 what? 1?
1 over 10 to the 1.
Beautiful. Now for base e, e is a very special number. It is equal to the sum of all the reciprocals of the factorials added up. It is related to the heavyweights of mathematics. E to the pi I plus 1 is 0. But e is roughly about 2.7. Now it's an irrational number, so the expansion continues just a little bit longer. There's the expansion of it, in case you're curious. I had a friend in grad school, Ed, that had e memorized out to 2,000 places.
Wow.
He didn't have much of a personality, but man, he had a good memory. When you evaluate, though, all you're doing to evaluate is you're putting into the input of x any of these numbers. So if I'm evaluating at 0, I'll put in this input of x as 0, and I would have e to the 0, which is?
Which is 1.
1. And then from here, you're just going to go ahead and write the numbers exactly. So e to the first is just e, which is 2.7-ish, right?
Yes.
Don't make me go backwards on the slides. 2.7-ish. It expands for a while. And then f of 2 would be e squared. F of 2.5 would be e to the 2.5. F of 3 would be e cubed. And if I wanted to know an approximate value, I can enter into my calculator e raised to the 3, and it would give me back, what would it give me back to 2 decimal places?
20.09.
Let me write that down. Beautiful. So if I want to look at evaluating e to the x at negative 2, I'd have e to the negative 2 written as a positive base, 1 over e squared. And the last one would be what? It would be
E to the negative 1.
which would be written as?
1 over e.
Beautiful. Thank you. Solve applications involving exponential functions in mathematics and sciences. When you're solving applications, you start with the basic exponential function f of x is equal to a times b to the x. The base is positive, it's not 1. But when you morph it into a function that we can use for applications in math and science, very often we use this form right here. A of t is equal to a e to the rt. And you may say to yourself, well, what is it exactly that I'm seeing? Well, this a is this a, but my input is changed from x to t, because very often t references time. And then you're noticing the fact that you do have a very different base. Your base is actually now e to the r. And a of t, which is the very last piece of it, a of t just refers to the amount after time t. I'm just going to write that out. So in terms of trying to understand this formula, all we do is we say, well, a is the initial value, and that's this a right here. R, which is this r right here, is the growth rate. And we use growth rate very carefully, because what that means is that you're taking a look at a change that's based on a percent change, because it's an exponential model. And you may say, well, what do you mean you're using it carefully? And what I'm referencing is that if r is positive, then we'll have growth. So if I go ahead and take a look at it, my exponential model, it would be growing right here. Right there would be the point 0a, and this is for when r is positive. If r is negative, then we have exponential decay. And so now my model looks a little bit more like this, where I have 0a and r is negative. So the problem we're going to look at deals with exponential decay. Radon 222 decays, pause for dramatic effect, but pause mostly because if we're looking at radon 222 decaying, we stop and say, whoa, 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 r is negative before we do anything else. And then we keep reading and says it decays at a continual rate, which is 7.3%, a percent change. So we have an exponential model. And so that r is 17%, 17.3%, 17.3 per 100%. So as a decimal, that's 0.173. Except we have to remember, well, that's not right. That's not right at all, because you just told me r is what? R is
Negative.
negative. So r is equal to negative 0.173. And we are being asked a question, right? We're being asked a question. We're being asked, how much will this radon decay to in 1 week? So it looks like we're looking for a of t. And if the growth rate is in terms of per day, 1 week is how many days?
7.
We're looking for a of 7. That's what we're looking for. So we come over here and say, well, what's my input? Input is time, and the time is measured in terms of the growth rate, which is per day. So here t is 7. Do you see the pieces that we're putting in?
I think so.
What's the only piece I haven't really accounted for? Kind of look at that model very carefully. Well, I sit here and pick a really nice color, maroon.
Is it the lowercase a?
Very good. This lowercase a. But what did we start with? How much?
500.
500 milligrams. Now we have enough information to answer the question. We're going to do what? We're going to substitute in a 500 right here. For r, we're going to substitute in what? We're going to substitute in for r what?
Negative 0.173.
Very, very good. And for my time, I'm going to actually go ahead and substitute in what? I'm going to substitute in a
7.
Beautiful. You can almost see the equation. She said, well, you'll write it out for me. And my response is, okay, well, hold on. We have a of 7, that's what we're looking for. The amount after 7 days, which is 1 week, is equal to little a, which is?
500.
Good. Times e to the r, and that's really your base. So that's e to the?
Negative 0.173.
Good. And in the exponent times what? Times
7.
Times 7. Now you're going to get a number here that's going to be irrational, so we're going to have to round it. But when you enter it into the calculator, just to remind you, you're going to go ahead and enter it very carefully. You want to enter 500. You want to enter E, and you want to raise it to, and in parentheses, negative 0.173 times, I'll put a big times symbol, times 7, and then you'll close the parenthesis. So when you do, you'll be able to find what that amount is after 7 days approximately. Let's go to the nearest tenth. Round to one place past the decimal point, and what do you end up getting?
So you'd have 148.9.
Beautiful, milligrams. Does that make sense? It is decaying at 17.3% per day. After 7 days, you went from 500 milligrams down to 148.9. It kind of feels correct. Thank you. Thank you. Solve applications involving exponential functions in business and economics. We know what the exponential function looks like. F of x is equal to a times b to the x, where the base is positive, it's not equal to 1. Often, in economics and business applications, we morph it to look like this particular function right here, which is a of t is equal to p e to the rt. And we notice, if we will, that our initial value, a, which is here, has been changed to p, which is here. And that means that our initial value is often referred to as a principal investment, an initial investment. And then we also notice something else. And what we notice is that our base here is now going to be e to the rt. And r is your growth rate or interest rate. And growth is not used as growth in terms of it's always going to grow. You look at the value of r to determine growth or decay. So if I go ahead and I'm just going to switch colors here, take a look at when r is greater than 0, what we have is exponential growth. We have exponential growth, and we have the point 0a right here. And if r is less than 0, if r is negative, we have exponential decay, and generally our graph looks something like this. So r is greater than 0, growth, r is less than 0, decay. So when we look at these investment type problems, very often we're given a time frame, that's t, an interest rate, that's r, and maybe we're asked to find an initial amount or principal, which is p, or maybe we're asked to find an amount after time t. In this particular problem, a person invests $250,000. It's $250,000. But that's what they invested. So you say, well, I know, you just said that, Jay. And I say, well, no, hold on. That's going to be my what? That's going to be my?
Your P?
My P, my principal. My principal is $250,000. That's what I just invested. And they're investing it at a nominal interest rate of 4% per year. So each year they're going to apply a 4% compound interest on it. So if we go ahead and take a look at our variables, we know that our interest rate, which is R, is 4%, 4 per 100, or 0.04. That's what R is. And we're compounding continuously. This formula, A of t is equal to P times e to the RT, is referred to as continuous compounding. Well, we're asked a question, right? We're asked a question. What we're asked is, what will be the value in 20 years? So we're looking at A of 20. We need to find that, the amount after 20 years. Which finally brings me to the very last piece of information, which I know you already know. The time frame is in terms of
Years.
years, and that's because of this word year right here.
Right.
And we're going to go ahead and look at t is equal to what? T is equal to?
20.
20. Beautiful. So that 20 is sitting right here. So you can see a equation that we're going to end up setting up. We're actually dealing with an exponential function. A of t is equal to p e to the rt, and when we make our substitutions, we're going to end up with this equation. We'll end up with a of 20 is equal to, so we're evaluating our function, So to find a of 20, what we're going to do is evaluate this function when t is 20. So a of 20 is equal to p, and p is what? P is?
250,000.
Beautiful. Times e to the r. R is what?
0.04.
0.04 times what? Times
20.
Times 20. Now, before we do anything else, one last check back at this particular problem. Will this value be more or less than $250,000?
Should be more.
Okay, so if it should be more, we're looking at exponential growth, right?
Yes.
Which means r should be what? R should be
Positive?
positive. Is r positive?
Yes.
Yeah, so we're on track. Now we just want to enter this into the calculator. We is actually you. You're going to enter it into the calculator. So when you enter it into the calculator, you're going to enter 250,000. You're going to multiply by e raised to, and then you're going to need parentheses, and you'll have 0.04 times, so I'll put a big multiplication symbol, times 20. And we're dealing with money, I suppose, right?
Yes.
So
Yeah.
the amount after 20 years will be approximately, because we're round to the nearest hundredth, but in terms of money, it would be exact. And what do you end up getting?
$556,385 dollars and 23 cents.
See if I wrote down what it is you said accurately. Beautiful job. So we have grown from $250,000 to over $500,000. And all we had to do was wait 20 short years. Thank you. Which of the following are exponential functions? And an exponential function could be written y is equal to a times b to the x. So the variable appears in the exponent, and the base must be positive and yet not equal to 1. So first thing I'm going to do is start with the function f, and I'm going to rewrite it. I'm going to rewrite it so that I'll distribute the 3 in the exponent. I'll have 4 to the 3x, and then 3 times negative 2 is negative 6 minus 6. Now I'm going to continue to rewrite my function, f of x is equal to, and I'm looking at my exponent as 3x plus a negative 6. When I multiply the bases, I add the exponents. If I'm adding the exponents, I can multiply the bases. So I have 4 to the 3x times 4 to the negative 6. Now I'm going to interchange the terms. I can multiply in any order. I have 4 to the negative 6 times 4 to the third raised to the x. When I raise a base to an exponent and raise it to an exponent, I can multiply the exponents. Well, now I'm thinking in reverse. Since the exponents were already being multiplied, I'm raising the exponent to the exponent. And notice the form. This is the form of a real number a times a base that's greater than 1, base is 64, raised to the x. F of x is an exponential function. I'm going to write yes. For g of x is equal to x cubed. To have an exponential function, my base has to be a positive number not equal to 1, but here my base is a variable. I can stop at that point and say, no, I do not have an exponential function. When I look at h of x is equal to 1/3 to the x. So h of x really is in the form of a times b to the x, because a is 1 and the base is 1/3, which is positive not equal to 1. So h of x is an exponential function. And lastly, when I look at j of x is equal to negative 2 to the x. But notice the base, negative 2, is not greater than 0. J of x is not an exponential function. Thank you. In 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. Now the population was growing exponentially. We want to write an exponential function n of t representing the population n of deer over time t. So in general terms, we have n of t is equal to a times b to the t. So what's our domain? That would be time. So let us choose time to be the number of years since 2006. What is the range? What is the output's going to look like? Well, that would be n of t, and that's the population of deer for a given value of t. Now, the ordered pairs would be in the form of t, n of t. So in 2006, that's 0 years since 2006 initially, n of 0 was 80. Initially, there were 80 deer. In 2012, so that would be t is equal to 6, because 2012 is 6 years since 2006, the population was 180. So we would have the ordered pair 6, 180. Now let's go back to our exponential function. A, that's the original population in this context. And I'll just abbreviate population. What was the original population? It was 80. So now we have n of t is equal to 80 times b to the t. So if I find the base, it looks like I'll have my exponential function. This is where the other ordered pair comes in. We know that when t equals 6, the population is 180, and I have enough information where I can solve for b. Substituting, I have 180 is equal to 80 times b raised to the 6th power. So let's solve for b. I'll divide both sides by 80, and reducing, we have 9 over 4 is equal to b to the 6th. So if I want to solve for b, I'll raise both sides to the what? 1/6 power. So it looks like we have 9 over 4 to the 1/6 power equals b. If we were writing our exponential function exactly, we would have n of t is equal to 80 times the base of 9 over 4 to the 1/6 times t. And that's the same as t over 6. If we were going to round the base, well, the base is approximately 1.1447 to 4 decimal places. So I could write my exponential function as n of t is equal to 80 times 1.1447, and I'd raise this to the t. Let's find an exponential function that passes through the points -2, 6, and 2, 1. So for my exponential function, I'm going to write f of x is equal to a times b to the x, and I'm going to write this function where a and b are approximated to 4 decimal places. Now notice, I don't have a value for a or b, and I don't have an initial point that my function passes through. So what I'm going to do is say to myself, well, if I know f of x is equal to a times b to the x, I'll substitute in my coordinate pairs, -2, 6, and 2, 1, and this will create 2 equations. And to find a and b, I have 2 unknowns, and I should be able to solve these 2 equations. So, for the ordered pair -2, 6, the output is 6, and the input, well, that's -2. And for the ordered pair 1, 2, the output is 1, and the input is 2. So I have two equations. 6 is equal to a times b to the negative 2, and 1 is equal to a times b squared. Two equations and two unknowns I should be able to solve, and I will with the substitution method. I'll take my first equation and I'll solve for a. Well, to solve for a, I'll go ahead and divide both sides by b squared. So I'll have 6 divided by b squared is equal to a. And so that is 6 over 1 over b squared. So that means a is actually equal to 6b squared. And if I just made a note off to the side, all we really did here was take 6 over 1, divide by 1 over b squared, and we simply inverted and multiplied. Now I'll go to my other equation, which is 1 is equal to ab squared, and I'll put in place of a 6b squared. So now I have 1 is equal to 6b squared times b squared. So I want to solve for b. I'll divide both sides of the equation by 6. So I have 1/6 is equal to, and at the same time I'll multiply b squared to b squared, and I'll get b to the 4th. So if I take the 4th root of both sides of the equation and solve for b to 4 decimal places, I find b to be the 4th root of 1/6, or to 4 decimal places, 0.6389. Now, the next thing I want to do is solve for a. And I'll come back to where we had solved for a earlier. And I know a is equal to 6b squared. So because we're approximating for b, we'll approximate for a. A would be 6 times our value of b, which is 0.6389 squared. And so a is going to be approximately 2.4492. So let's see, we have an approximation for a, we have an approximation for b. All we have to do is go back to our function, f of x is equal to a times b to the x, and replace a with what we found it to be, and replace b with what we found it to be. So it looks like f of x is equal to 4 decimal places, a, which is 2.4492, times b, which is 0.6389, to the x. And we have our function. Find the graph of the exponential function whose graph is shown below. Now the first thing I want to do is say my exponential function would be y is equal to a times b to the x. So I have to find a, which is any real number other than 0, and b, which is a base that's positive and not equal to 1. The way I'm going to do this is identify 2 points on the graph. One point, right here, has coordinates 0, 3. And the other point, right here, has coordinates 2, 18. Now let's talk about the point 0, 3, which is here. That means the y-coordinate is 3, and the x-coordinate is 0. So if I plug that into my standard form, I get 3 is equal to a times b to the 0, which is 1. That means I just found the initial value a, which makes sense because that's my y-intercept. So I know a little bit more about this exponential function. It's y is equal to a, which is 3, times b to the x. Next, I want to find the base. So I'd like to turn my attention to my second point right here. And notice that when the y-coordinate is 18, then the x-coordinate is 2. And I'll be able to solve for the base b. I'll divide both sides of my equation by 3. Well, 18 divided by 3 is 6. So 6 is equal to b squared. And if I take the square root of both sides of the equation, I find that base is equal to the square root of 6, or 6 to the 1/2. There's my exponential function. Y is equal to a, which is 3, times my base, which is the square root of 6, to the x. Thank you. Let's evaluate this function, 5 times 3 to the x plus 1. We'll evaluate this function at 2. So the first thing I'm going to do is write f of 2 is equal to, and I'm going to put a 2 in for x, so it's going to go in the position of the exponent. So I have 5 times the base is 3 raised to the 2 plus 1. So I'll be very careful to follow the order of operations. First thing I'll do is add 2 plus 1, and that gives me 3. So now I have 5 times 3 cubed. Now the only thing being cubed is the 3 itself. So 3 cubed is 27. Now I have 5 times 27. And 5 times 27 is 135, and I'm done. My input is 2, my output is 135. Write equations of exponential functions. Sometimes we're given information about an exponential function, but we don't know the actual formula. Now we know the general form, f of x is equal to a times b to the x. And what we have to do to find that exponential formula is find a and b. Now a, that's just the initial value, so that if you put in a value of 0 for x, b to the 0 is 1, and the function kind of breaks down to f of x equals a. And then if you go ahead and take a look at b, well, b is the base. So our goal is to find a and b and substitute the values into the function. Now the game plan is very straightforward. First of all, the bases have to be positive and not equal to 1. We want to find a and b. Now, what we're going to be given is 2 data points. Here's the best case scenario. One of the points, see if I can switch colors here. Okay. One of the points is 0a, so we know a outright. If that's the case, then using a, we can put the second point into this function and we can find b. In other words, we give you a, you find b by using the other point. The likelihood you'll see that today, yeah, that's not going to happen. It's highly unlikely. You're going to see the more difficult case. The more difficult case is what? The more difficult case is, well, neither of the points have this form. You're given just 2 points. And what you'll do is you'll substitute both of the points into this formula, kind of one at a time, creating 2 formulas. And then you'll have to solve those 2 equations simultaneously for a and b. And again, we're looking for a and b. Let's go ahead and find an exponential function that passes through the following 2 points, 1, 2, and 3, 2/9. Now notice neither point is in the form of a0. So first thing I'm going to do is I'm going to write f of x is equal to a times b to the x. And I'm going to start by just doing nothing more than taking each point separately and substituting it into the formula. And again, here's the x value, here's the f of x value. So when I do this, f of x is 2. This is equal to a times b to the first. Let's do the same thing. That seemed awfully fun. Let's go ahead and look at the second point. And again, here is x, and here is f of x. And we'll substitute in. So the output is 2/9, and that's equal to a times b to the what? B to the?
To the third.
To the third. Now I want to solve those 2 equations to find a and b, and the way I'm going to do this is with substitution. I'm going to come over here, and I'm going to do a quick solving for a. You say, well, that's not so bad. I'll divide both sides by what? Both sides by?
By a?
Okay, so I want to find a.
Right.
I want to isolate a, so I'll divide both sides of the equation by?
By b.
By b. So this gives me 2 over b is equal to what? Is equal to?
2a.
2a. Very good. And that 2 over b, I'm going to go ahead and put that right here. That's what I'm going to do. So now I'm going to bring over my equation that I've written in Blue, 2/9 is equal to A, which I'm going to write as what? As
2 over b.
and multiply it by what? By
b cubed.
by b cubed. So let's talk about this for a moment. I got 2/9 is equal to 2 times b cubed over b. One of the b's would cancel. Looks like 2/9 is equal to what? Is equal to 2 times
b squared.
b squared. And I want to solve for b and then go back and find a. So I want to isolate b squared. What will I do to both sides of the equation?
Divide by 2.
Divide by 2. And here the 2's cancel, so I want to say I end up with what? I end up with 1/9 is equal to
b squared.
b squared. And if I take the square root of both sides, I guess b would be equal to what? B would be equal to?
1 over the square root of 9.
And what is 1 over the square root of 9?
1/3.
1/3. And notice I'm just taking the principal root, because I know that the base has to be positive and not equal to 1. Now I have b, so I'm going to box it. That's kind of a big deal. I have this thing right here. That's what I have. So next thing I want to do is find a. Now to find a, what do I know? And your response is, what you know, Jay, is that a is equal to 2 over b.
Right.
So I'm going to substitute in b, and b is what? B is
1/3.
1/3. So now I have a is equal to 2 over 1 over 1/3. Why did I write it so quirky?
I'm not sure.
Okay, because when you divide fractions, what do? You actually,
You multiply by the reciprocal.
so it looks like a is actually equal to what?
To 6 over 1, which is 6.
Beautiful. That's kind of a big deal, because now I have this piece here. Now you can turn around and read me my exponential function. My exponential function is f of x is equal to a, which is
6.
times b, which is
1/3
raised to the
x.
x. Thank you. Solve applications involving compound interest. I want to look at a problem so I can start to see a pattern to generate my compound interest formula. And I follow this logic. Suppose we want to invest $100 at 10% interest, and we're going to go ahead and take a look at it being compounded once a year for 2 years. So if I said, what was my amount in year 0? You'd say, well, Jay, that's $100. If I said, what is my amount in year 1? You would say that's $100, but because we're compounding at the end of year 1, it would be plus 10% of $100. That makes sense.
Yeah.
So if I go ahead and say, well, what does that mean? If I factor out the $100, that would leave a 1 with the first term and a 0.1 with the second term. You'd say, so? And I say, no, hold on. How about if I looked at the amount after 2 years? I would have that $100 times 1 plus 0.1, and then I would take that amount, which is $100 times 1 plus 0.1, and multiply by 0.1. I take 10% of that. And when you look at it very carefully, you say, well, gosh, you can factor out that 100 times 1 point plus 0.1. So now I have $100 times 1 plus 0.1. And when I factor that out, I have left over 1 from this term and a 0.1 from this term. And I end up after 2 years, let me say that again, after 2 years, $100 times 1 plus 0.1 squared after 2 years. And I notice something very specific. And what I notice is that I have my amount I invested here, and then I have my interest rate here that I compounded once a year. And then I have the number of actual compounding periods here. And the only catch is when I look at my compound interest formula, we're going to compound generally at random time intervals that will be given to us. Random in that it won't necessarily be once a year, it'll be these other time intervals. So when I look at my compound interest formula, I'm looking at it with a very specific eye. I'm saying A of t is the amount that I'll accrue after so much time has passed, time t. I'll go ahead and take a look then at t being my variable. So when I look at my variable t right here, I notice that it appears here and here. And then I'm going to go ahead and say for my starting amount in the account, this is my principal, that's like my $100. My interest rate in the account, that's R. But then I take R and divide by the number of compounding periods per year, N. When I look at this very carefully, when I take a look at R divided by N, I see that I would have that hypothetical 10% if I was compounding 4 times a year divided by 4, because that means 4 times a year I don't get 10% interest, I get a fourth of 10% interest. And for compounding periods, that exponent nt, that's the number of times I compounded each year times the number of years. 4 times a year for 5 years. All right, that was 20, and that's n times t. As far as that compounding periods n, it leads right into some information that we know, which is just in terms of vocabulary, annually is once a year, semi-annually is 2 times a year, quarterly is 4 times a year, monthly is 12 times a year, and these are all the values that n would take on. N would be 1, 2, 4, 12, and so on. So if you were compounding daily, hourly, by minute, or by second, you would go ahead and use those values for n. Here's our problem. We're going to invest, so let me see if I can switch to pen mode, $10,000 in an investment paying 2% interest compounded quarterly. And we want to know how much will be in the account. So how much will be in the account in 5 years. Let's write down our formula. We know our formula. Our formula is A of t is equal to P, which is principal, times 1 plus R over N, which is the interest rate as a decimal divided by the number of times you compound a year, raised to NT, which is really just the number of compounding periods, but it's the number of times you compound per year times the number of years. Let's identify a whole bunch of stuff. What is this $10,000 right here?
That would be principal.
All right. Let's go ahead and take a look at what is the 2% written as a decimal. Which of these variables would that be?
The rate?
Okay. Let's go ahead and take a look at quarterly. What would this quarterly refer to?
Would that be n?
That's the number of times compounded per year, n. And then this is a weird little question, but how much will the account be worth? What is that?
A of t?
A of t. And in this case, it'll actually be A of the value of t, A of 4, huh? And lastly...
Wouldn't it be of 5?
Oh, it'd be a 5. Why did I say 4? Any responses? I don't know. Okay, A of 5. Good. And how about if I take a look at, which now sets up very well the very last question, what would my 5 represent?
T.
T. So T is 5. So that's what we're substituting in. So let's go ahead and substitute in. Back to pen mode. We're going to have P is what? P is
10,000.
10,000. R is what? R is?
R is 0.02.
Very good. N is what? N is?
4.
4. N is 4. T is?
T is 5.
5. So if I write down A of what? A of?
A of 5
Is equal to what? Is equal to?
equal to 10,000
Good.
times 1 plus 0.02 over 4.
Very good.
And then that is all raised to the 4 times 5.
4 times 5. I like the way you said that. So we want to calculate this out. Does it seem right? You have the principal of 10,000. 1 plus 0.02 over 4 means you're taking your 2%, distributing it over 4 times a year. so that's a quarter of it each time. And the number of periods is actually 20, 4 times a year for 5 years. The formula should make sense to you. Now when you enter it into the calculator, you can enter it all in one fell swoop. Swoop word, one fell swoop. You can enter 1,000, it's not 1,000, you can enter 10,000 times 1 plus 0.02 divide by 4 and raise it to the 4 times 5. And when you do, out to the nearest penny, can you tell me the answer, please?
Yeah, I got $11,048.96.
Beautiful. 11,000, you said $48.96.
Exactly.
We started with how much?
We started with 10,000
We ended up with?
with 11,048
And
96 cents.
thank you so much. Thank you. If we invest $3,000 into an investment account that pays 3% interest compounded quarterly, we need to find out how much will be in the account in 10 years. So we have a compound interest formula that we know. We have A is equal to P times 1 plus R over N, all raised to N times T. Now as I look at my word problem, I'm investing $3,000. That's my principal. What are the terms? Well, I have an interest rate of 3%, and it's compounded how frequently? Looks like 4 times a year. I need to know how much is in the account, so I'm looking for A, and the time frame I have is 10 years. So let's see if we can substitute in. Looks like our principal is 3,000. Our rate is 3%, which is 0.03. The number of times a year is 4. And we're looking at 40 compounding periods, 4 times a year for 10 years. Do you see a formula in front of you? It looks like we have our future amount to be equal to 3,000 times 1 plus 0.03 over 4 raised to the 4 times 10. And so if I go ahead and take out my calculator and enter it into my calculator, it looks like this amount is, and I'll write this as approximately $4,045 and rounded to 2 decimal places to give us cents and 5 cents. That's how much will be in the account in 10 years. A person invested $1,000 into an account earning 10% per year, compounded continuously. How much was in the account at the end of 1 year? So I'm going to underline the time frame of 1 year. Now, because we're compounding continuously, we're going to use the formula A is equal to P e to the RT. And let's identify what we have and what we need to find. A of T, or A, is the amount of money that will accumulate after so much time has passed. This is what we're looking for. We want to know how much was in the account at the end of 1 year. P is the amount that's invested, or the principal, and this would be 1,000 because $1,000 was invested into the account. R is the interest rate, and we know the account is earning 10% per year, and so if we change 10% to a decimal, that's 0.10. And T is the length of the investment. In this case, T is 1 because the investment is for 1 year, and T will be the length of the investment in time. So let's substitute into our equation. A is equal to P, which is 1,000, times e to the r, 0.10, times t, which is time, and that's 1. So if we simplify, we have 1,000 times e to the 0.1. And if I enter this onto the calculator and round to the nearest 2 decimal places, we end up with 1,105.17. In other words, at the end of 1 year, the account is worth $1,105.17. Radon 222 decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon 222 decay to in 3 days? Well, my exponential decay function is a of t is equal to a e to the RT. And if we do have exponential decay, which we do, we know r is negative. So let's identify which variables we were given. We know that we decay at a rate of 17.3% per day, so r is equal to negative 0.173. We know initially there are 100 milligrams, so that means A, the initial value, is 100. And we want to know how much of that 100 milligrams will decay to in 3 days. So we know T is equal to 3. So let's substitute in. In place of R, we'll substitute in a negative 0.173. In place of A, we'll substitute in 100. And in place of T, we'll substitute in a 3, both here and here. So the amount that we have left over in 3 days, we'll write as A of 3. And this is equal to 100 times E raised to the negative 0.173 times 3. And this is approximately 59.5115 milligrams. Thank you.